So, looking at decision version D, section A, which is looking at building a rockery. We do not actually need this I here. This wouldn't be here. It's not needed, as having N. Now N tells us we have to have M. So N means we had to have had M. M means we had to have had K. And K means we had to have had I. So actually, that I wouldn't have ever been written there. Okay, right. What we've got is our tasks, the duration, and what has to come first. So, activity network. So, first off, we have A, and A has nothing before it but a duration of 1. We've got the rocks, nothing before it, but takes 0.25. We've got C, nothing before it, takes 0.25. And D, nothing before it and takes 2. So what we have is the beginning of our assembly of our network. Each one is going to need a box around it and 3 boxes at the bottom.
Everything on the plate's cooked really, really well. Your duck leg actually is moist. Then you roast it and then finish it off.
Okay, now E. E has to wait for A. So E is going to come out of A.
Your duck is soft, your rice is nicely cooked. I like the flavour of your sauce. There's something almost mutton.
And E takes 1 hour.
Maybe you just don't like shrimp paste. No, I love shrimp paste.
F.
That's it.
F comes out of E, has to wait for E and takes 1. So we've got F next.
I'm sorry, Greg, but maybe put too much shrimp paste in it.
Then we've got G, and G has to wait for F, but nothing else. And G takes 0.5. H waits for G. So what we've got looks like a predominantly linear path of what we're doing. So I laying our flagstones, I comes out of H, and that is 1.5. J also comes out of H, so we have J as well, and that takes 0.5. K comes out from I and from B, so I has to wait, so where are we? K has to come out from B and I, and K is 0.5. L comes out of C.
I thought he used so much of that You said quite rightly, not enough sauce.
So L is 0.5. M comes out of L and K. So if we put M a little bit further along, and that can then come out of K and out of L. N comes out of M and D. And N takes 1 and didn't fill in the bottom of M. That takes 0.5. So N comes from M and from D. O comes out of J. So O can come over here. So O comes out of J and is 0.5. P comes out of O and I. So P comes out of O and I. And then Q comes out of N. Oh, didn't fill a little bit in. And then Q comes out of N, and that is 1. And then we have an end, and that goes into our end, and that one also goes into our end. Okay, so that is pretty much everything. So going forwards, earliest start times. There is nothing before A. So because there's nothing before A, we can put a 0 in here, nothing before B, nothing before C, and nothing before D. E has to wait for A. So if A can start at 0 and takes 1 hour, then E has to wait that 1 hour before they can start. F is going to wait the hour that E waited and the hour for E to do their thing. G is going to wait... Oh, no, that's a 2. You're an idiot, Nicola. G is going to have to wait the 2 hours that F waited and the hour for F doing something. H is going to have to wait the 3 hours that G waited and another 0.5, so we get 3.5. So I is going to have to wait the 3.5 hours that H waited and another half an hour, so that's going to be 4, and J is going to have to wait the same time. Going across, P is going to have to wait for I, so P is going to have to wait for I to finish, so the 4 hours and another 1.5. So that is going to be 5.5. P is also going to have to wait for O. O had to wait for J, so O is going to be 4.5. 4.5 and 0.5 is just 5. So P has to wait for both of these things to have happened. So if you can't start before both of these have happened, you have to wait for the slowest person before you can do it. So I also goes into K. So we've also got a 5.5 going into K, and we've got a 0.25. So have to wait for the slowest one. Slowest is going to be 5.5. M has to wait for L. So L is going to have to start at 0.25. Add the 0.5 gives us 0.75. But we've got 5.5 and 0.5, so we've got 6 here. 6 hours is definitely slower than 3/4 of an hour, so we're going to have to wait for that. We've got 0 and 2 coming into N, and we've got 6 and 0.5. So this one's going to be the slowest. So we have 6.5, 6.5 and 1 is 7.5. So we've either got 5.5 and 1, which is 6.5, or we've got 7.5 and 1, which is 8.5. So we are going to end at 8.5. So that is all of our earlier start times. You do not need to write these numbers on the edges. They are just vague working out. Doesn't need to be there. So if we are going backwards, we start with this 8.5. So we have 8.5 that can go in here and 8.5 that can go in here. So 8.5 is the deadline here. So the deadline that P gives to O is going to be their deadline and the amount of time they need to work on it. So what it is effectively is 8.5 take away 1. So 8.5 take away 1 is going to be 7.5 is the deadline they give these guys, and the deadline that they are also going to put into I. But I is going to be given its deadline by somebody else as well. So if we come down here, we've got 8.5 take away 1 is 7.5. We've got 7.5 as our deadline. So N is going to need to take an hour. So the deadline they pass forward is going to be 6.5, because 7.5 take away 1 is 6.5. And that's the deadline that they're going to give both people. So the deadline M hands out, their deadline is 6.5. It's going to take them 0.5. So the deadline that they'll pass on is going to be 6. So L's only got one person feeding in, K's only got one feeding in. So K, deadline of 6, takes 0.5 to do their work, so they need everything finished and to them by 5.5. So we've got 2 values here for a deadline. So if your deadline that you are given from one person is 7.5 and one person is 5.5, if you go with the 7.5, this guy is going to be running 2 hours late. If you go with 5.5, both of them are going to be happy. So we always choose the earliest deadline. So 7.5 take 0.5 is 7. So coming in here, we have 7 take 0.5. So we've got a deadline coming in at 6.5. But we've also got a deadline of 5.5 take away 1.5, which is 4. So we've got a deadline coming in here of 4, and 4 is smaller than 6.5. When we did this one, we had 6 take away 0.5, so deadline in here of 5.5. Here, 6 take away 0.5 gives us 5.5. So going along here, 4 take away 0.5 is 3.5. 3.5 take away 0.5 is 3. 3 take away 1 is 2. And 2 take away 1 is 1. Next thing that we are going to need to do is a critical path. So, critical path. What we're looking for with a critical path is whether or not the numbers work. So, 0 plus 1 is 1. This one is critical. 0 plus 2.5, 5.5. That's not true, so it's not critical. 0 plus 2.5 is 5.5. Not true, not critical. 0 plus 2 is 6.5. Not true, not critical. So because this one isn't critical, this one can't be. If this one is critical, everything it goes into is going to be critical until the next junction. So we know that that's critical, that's critical, that's critical, that's critical. Then we have options. So 4 plus 0.5 is 7, not critical. 4 plus 1.5 is 5.5, critical. We've then got another junction, so we're going to have to check. So 5.5 and 1 is 8.5, not true, not critical. 5.5 plus 0.5 is 6, that's true, that's critical. Then we've got this one, so 6 plus 0.5 is 6.5, 6.5 plus 1 is 7.5, 7.5 plus 1 is 8.5. So we have our critical activities. So our critical activities are A, E, F, G, H, I, K, M, N, Q. And what we are then asked to do is find the total duration of the project, and that is this, our end value, and the critical path. So our critical path is A, E, F, G, H, I, K, M, N, Q, and it has a length of 8.5 hours. Okay, so next thing that we are looking at is a cascade diagram. So a cascade diagram can also sometimes be called a Gantt chart.
But I guess for me, also in competition, I've been sort of playing around with different cuisines, and I didn't want to start here.
So it doesn't matter which way it's referred to, it's the same thing. Now, they will give you graph paper for this because they want it to be relatively accurate. So, it will not normally have numbers or anything useful on it, but it is at least there. So 8.5 hours, we've got 1, 2, 3, 4, 5, 6, 7, 8.5, that's fine. So timing, we can have 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay, a cascade diagram will traditionally have A at the top, going down to Z, but it's not actually a problem if you do it upside down. So, for ease of doing stuff, we have point A. So A starts at 0, goes one box along and finishes at 1. So, what we've got for A is going to start at 0 and go along one box and finish at 1. So because that is a critical bit, it has no float. Then if we look at B, B starts at 0, is a quarter of a square long. So B starts at 0, goes along a quarter, and has to have finished by 5.5. So it has to have finished by here. So this is the bit you're doing, and this bit here is what is known as float time, and that is put in with a little dashed line, which means that the solid bit at the beginning can happen any time between our beginning point here and our end point here. So C, exactly the same. Start at 0, finish at 2.5, but goes up to 5.5. So we need this first quarter in as solid, and then for the rest of it we are looking at a little dashed line. Although technically there are a couple of options as to the way this is set out, it's useful to have the bits on the end. Some people will draw this as a box. It genuinely doesn't matter. Okay, and for 6, and for D, starts at 0, goes along to 2, that's our solid bit, finishes at 6.5, which is over here. So, first bit is how long it takes, and it takes from 0 to 2 because it's 2 hours, and then it's got to have been finished by 6.5, so we have a float that is actually 4.5 long. Then we have E. So E is on our critical path, so we're not expecting it to have any float. It starts at 1. It goes along 1 square. And the last bit finishes at 2, so we don't have to go any further than this. F starts at 2, goes along 1 square. So F starts at 2, goes along 1 square, and finishes at 3. So again, no float. G starts at 3, and G goes along by 0.5 and finishes at 3.5. Again, no float. Okay, so we have G, then we have H on our next one, and H starts at 3.5 and takes 0.5, finishes at 4. Then we have I. I starts at 4. I goes along 1.5 and finishes at 5.5.
You don't cook a great deal of fish?
No, I don't know.
Is that making you nervous?
So nervous, yeah. Really.
J starts at 4, goes along 0.5 and finishes at 7. So starts at 4, goes along 0.5, but finishes all the way over here at 7. So this bit is going to be solid because that's when we're working, and this is our float, which is the time, which is a little bit flexible. So we've got J, then we've got K, and K starts at 5.5. So starts at 5.5, goes along 0.5 and finishes at 6. L. L is way back here. So L starts at 0.25, which is here. Takes half an hour. So goes up by half an hour and finishes by 6, and 6 is over here. So we've got this little bit of work, but we have an awful lot of float. Okay, so that's L, and then if we head back over this end, then we have M. So M is going to start at 6, goes along 0.5 and finishes at 6.5, so no float. N starts at 6.5, goes along 1, finishes at 7.5, no float, N, O, O starts at 4.5, so 4.5 is there. O starts at 4.5, goes along 0.5, but finishes by 7.5. So we are going to need this bit to come in as float.
as well as some of the country's leading chefs and restaurateurs.
Okay, so P. P has to start, or can start at 5.5. So P can start here, because it has to wait for I, which finishes at the same place. It goes along by 1, but it can finish, has to have finished by 8.5. So, solid bit, and then the dots for the float. And lastly, we have Q. So Q is starting at 7.5, which is here, takes 1 and finishes at 8.5. So a relatively nice double check that we can do is looking at our critical path. So our critical path went A, then E. So as soon as E finishes, we do F. As soon as F finishes, do G. As soon as G finishes, do H. As soon as H finishes, do I. Once I finishes, we have to start K. K finishes, start M, then N, and then Q. So all of our things that don't have any float are on our critical path, and they go neatly from one up to the next right the way across, and it all fits in. So that bodes well for our critical path. Okay, question 2, we are being asked to use Dijkstra, and it's from SS to GA. So, first step, we're starting at SS, so we want to circle 0 there. Next bit. So the next bit, we are now into the algorithm. So, algorithm says box the smallest and then 1 step in each direction. So 1 step is 5, 1 step is 5, and 1 step is 10. Algorithm says box the smallest. So we've got these 2 5s, doesn't matter which we choose. So if we pick this one first, 4 plus 5 is bigger than 5, so we'll stick with the 5 we've got. We can't go anywhere else, so box the smallest, which is this 5, and 1 step in each direction. So 5 plus 3 is 8, 5 plus 6 is 11, which is bigger than 10, so we'll keep the 10 we've got. Can't go anywhere else, so box the smallest. 8 plus 8 is 16, 8 plus 8 is 16, which is bigger than 10, so we keep 10. 8 plus 7 is 15. Then we box the smallest, so that's this 10 up here. 10 plus 7 is 17. 10 plus 9 is 19. 10 plus 7 is 17. 10 plus 9 is 19. 10 plus 8 is 18, but we've got a 15 here, so we'll stick with the smaller one we've already got. Then we box the smallest. So smallest we've got is this 15. So 15 plus 8 is bigger. 15 plus 3 is 18. 18 is smaller than 19. So we cross 19 through neatly so that we can still read it. And we put an 18 in. There's a mark going to be available for having done that crossing out of that 19. Smallest thing we've got is this 16. So 16 plus 14 is going to give us 30. 16 plus 7, bigger than 18. And we can't go anywhere else. So we box the smallest, 17. 17 plus 6, bigger than 19, can't go anywhere else. Next 17. 17 plus 1 is 18. 17 plus 9, bigger. 17 plus 4 is 31. So we've now got a route that we could go that is 31 minutes, but we want to find out if we've got anything smaller. So we box the smallest thing. So if we box this 18, 18 plus 8, bigger than 18, can't go anywhere else, box the smallest. 18 plus 15 is 33. 33 is bigger than 31, so we don't do anything with it. Okay, so we then look for and box the smallest, and that's this 19. So 19 plus 10 is 29. And then we box the smallest, which is this 29. So the total length, so we have a length of 29. But how did we get there? So 29 take 10 is 19. So we've come along here. 29 take 14 isn't 17, so it wasn't that. 19 take 9 is 10. 10 take 10 is nothing. So the route that we used was SS to SP to LB to GA. Actually, a question 2. So we are doing Chinese postman, and we are doing same start and finish. So our start and finish is at the same place. So first off, we are asked to find the minimum length of his route. So there's a really systematic way that we do this. First off, we find the odd nodes. So ones with an odd number of things coming out of them. So we've got an odd node at GA because it's got 3. We've got an odd node at SS because it's got 3. We've got an odd node at BA because it has 5. And we have an odd node at BP because it also has 5. So first off, we identify our odd nodes. So we have odd nodes. So our odd nodes are SS, BP, BA, and GA. Next, we need to pair these up. So for our pairs, we could have SS and BP. We could have SS and BA. We could have SS and we could have GA. Okay, so if we have SS and BP, then the 2 we have left over are these 2. So BA, GA. If we have SS and BA, the 2 we have left over are BP and GA. If we have SS and GA, the two we have left over are BP and BA. So we've sorted out our pairs, and now we need to find the distance between them. So the distance between SS and BP, we could go this way, which would be 19, but we could also go this way, which is 18. And then we've got to go between BA and GA. I think that's going to be that 14. So, SS to BA, we've got a 10 and a 7, and anything else is going to be more. So we've got 17, and then going from here to here, we've got 23, regardless of which way we do it. Then lastly, we've got to get from SS to GA, which is kind of long. So we could go 10, 9, because 9 is shorter than that bit, and then 10, because that's our shortest bit there. So if that's 29, and BA to BP, we've got 9. So if we add these up, we get 32, we get 40, and we get 38. So we then need to know which is our smallest one. So this one is our smallest. So for our Chinese postman problem, we need to add our smallest to the total of all of the roads, and the total of all of the roads, we are told, is 199. So that one is our total. And hopefully if we add those two together, we get 231. And these are in minutes. So that sorts that. Okay, so how many times does he pass the palace? So the palace is this one. It's SP. So we need to know how many times do we walk through the palace. So if we just look at this, we can check that SS to BP, that doesn't go through here because we went through this way and the other was that bit. So we're just worried about the roads that are already there. So if we walked in on that road, we'd walk out on that road. So that's going through once. If we walked in on this road, we could walk out on this road. So that's twice. If we walked in on this road, we could walk out on this road. So that's 3 times. And if we walked in on this road, then we could walk out on this road. So that's 4. So for 3A, how many times do we pass the palace? We walk through it 4 times. How many times do we go over the bridge? So on this system, when we walked it, we had to repeat this section and this section. So we effectively did that line twice, and we also did walking along here and up here a second time. So with that bit, we walked once along it on our pink line for our repeat. We walked once over it, going across from PP to SP. And we walked once across it, going from SS to UG. So we walked across it 3 times, even though there's only enough lines there for 2. Okay, part C. We are now told if we can start and finish anywhere. So this is a different start and finish. We want to know the length, and we want to know the start and the finish. So what we are allowed to do is we can look at this and we can choose one of these numbers to be our repeat. So if we choose this one to repeat, then what we are doing is for 3 part C, we are going to repeat. So we'll repeat this pair, BP, BA. So our Chinese postman problem becomes 9 plus our total. So that is 108. And we're also asked about our start and finish. So if we've repeated these 2, what we've got left is a start and a finish. So we can start at either one of these. So if we start at SS, we're going to say we've used that one, then we'll finish at GA. Use that one. Question 4. We have a council. They want to connect an electrical network linking every location in the city using Prim's algorithm. If we are using Prim's, we need to know where we start. So if we start at SP, so we'd need to be told where to start. So we've got a value that I just didn't type in at the time. So if we start off at SP, we can look at everywhere that is attached to SP. So we want the shortest one. So the shortest thing coming out of SP is 6, and that is SP to PO, and that is 6. So we now know everything that's coming out of here as well. So the smallest thing that we've got coming out of there is 3. So we have PO to UG is 3. So we now know about everything coming out of here. So the next smallest thing is this 4. So we go PO to PP, and that is 4. And the next smallest thing coming out of those, it's going to be one of the 5s. So we could choose either of these 2. Out of neatness, we'll choose this one. So we've got PP to SS is 5. Okay, so we're now looking for the next smallest. So the way you do this will actually impact on where you go. We could choose this 7, or we could choose this 7, or we could choose this 7. And all of those will give us a slightly different path. So if we come up here first, we've got SP to MN is 7. And now we've got an option to come out of here, which is 6. So we have MNLB, which is 6. So the other things that we've got, we can now choose out of here, but these are bigger, so we're going to have to come back to one of our earlier 7s. If we come out of here, which we could have done at the earlier bit, we've got SP going to BA, which is 7. Okay, and from there the smallest thing that comes out is this 1. So we could then do BA MF is 1. So next bit that we can do, we're going to have to return to one of the other 7s. So we can go here. So we've got UG to PA is 7. Then we've got this 3, which is the next smallest. So we've got PA to BP, and that is 3. Next smallest thing is 7, coming down here. So we've got BPSC, also 7. So you could have gone into this at any of a couple of points. You could have come in and done that order. You could have come in, done that order, or you could have come in and done that bit. So these 3 sections can appear in any order. And then we go back, so we don't want any loops, so we're now looking back up here. So LB to GA to join on to something new. So LB to GA, and that is 10. So we've got our list, and we're going to want a total. So we add those up, and hopefully we get something nice. This feels a lot like a calculator moment. So 6 plus 3 plus 4 plus 5 plus 7 plus 6 plus 7 plus 1 plus 7 plus 3 plus 7 plus 10. So hopefully that gives us 66. So if you had used Cascade, so Cascade and the first 5 arcs. So first 5 arcs with Cascade, you pick the smallest one regardless of where it is. So the first 5 arcs we would have picked are this one at 1, this one or this one at 3. So those 2 would be appearing in either order. Then we're going to do 4. And then we are going to choose 5. And that'll be our first 5. So first 5 would be BAMF, which is 1, then BPPA, which is 3, then POUG, which is also 3, so these 2 can come in either order. Then POPP, which is 4, and PPSS, which is 5. So there's the first 5 we would have chosen. what would have been the last two? So the last two are going to be our biggest two, and our biggest two are the 10 and any of the 7s. Doesn't matter which. So that was for 4B, and then 4C would be LBGA would be last, and then any of the 7s, so BPSC is going to be second to
Don't know why you put some sort of
last, but this one could be any of the 7s.
However, the raviola is a thing that completely yummy.
A deep fried lemon dumpling.
Okay, so question 5. We are starting off with the nearest neighbour algorithm. Nearest neighbour just means that you go to the closest thing. So we always go to the closest thing unless we've been there. So if we have to start at GA, then the closest thing to GA is the 10 at LB. The closest thing to LB is MN at 6. The closest thing to MN that we've not already been to is SP at 7. SP. The next thing we're going to go to is BA, because that's the closest that we've not been to. Then at BA, the only place we've got left to go is MF, so we're kind of going to have to go there, and hopefully it's also the closest. Okay, so we've been everywhere. The next thing we need to do is go home, and home is GA. So we need to know how far it is from MF to GA, and that is 15. So nearest neighbour, we are then going to need to add these up. So 14, 15, 30, 46. Okay, so next bit, using this tool. So using this route. So we are using this. So we are starting here, and because we're using this route, we are going LB. Our route takes us to MN, which takes us to SP, which takes us to BA, which then takes us to MF, which takes us to GA. Now, that's fine stopping here when you started at GA, but where we go from GA is LB. So we've got the tour starting and finishing at LB. Next, we are looking at figuring out a lower bound. So a lower bound, we are told we are deleting GA. So that means we need to include the two shortest ones from GA. So looking at GA, there is a 10 and a 14. So we could go LB, which is 10, or we've got BA, which is 14. So that's 24. The other bit of the lower bound is prims on everything else. So if we start by numbering our first column, highlighting our first column, crossing out our first row, then we look for the smallest thing that is currently highlighted, and that is this 6. So we've got LB, MN is 6. So we've just gone to MN. So this is the second place we've gone to, so we label it with 2, highlight it, cross it out, and then we're looking for our smallest thing. Our smallest thing in our highlighted bits is this 7. So we have MN to SP is 7. So we've gone to SP. That's the 3rd place we've added. So we are going to highlight it, cross it out, and then look for the smallest thing. The smallest thing is this 7. So we have SP to BA, and that is 7. So we went to BA, so that's the 4th place we've added. So we will highlight the column, cross out the row, and then look for the smallest thing we've highlighted, which is this 1. So we get BA to MF is 1. So our total is 7 and 7 is 14, 21. So we wanted a lower bound. So that's going to equal 21 plus 24. So that is 45. So between which times will the optimum tour lie? It's going to lay between 45, which is our lower bound, 46, which is our upper bound. Inequalities go in, pointing towards the small one, small end, small number, big end, big number. And we'll call our tour T because we're not very imaginative. So for a second example on travelling salesman, we are starting this time at BP. So if we want an upper bound, it's nearest neighbour. So we start at BP. Closest thing is PA at 3. Closest thing that we've not been to is UG at 7. Closest thing is going to be one of the 8s. So we may as well go with this one, and that is at SC, is 8. So we're now at SC. Smallest thing is BP, we've been there, also been to PA and UG, so we're going to go to MF because that's 14, which is slightly smaller. MF goes to BA is 1. So we've now been everywhere, so have to go home, and home is BP this time. So BA to BP is 9. So adding those together, we've got 10, 20, 34, 42. So our upper bound is 42. And then we're looking at a lower bound. So if we delete BP, then we have to include BP